Hello everyone. I did one thing just a few minutes ago. I updated the slides just slightly to hide the first slide after the title slide, which was things to do to prep for Project 2. That was just a little bit of off timing. That was the right timing if we had been in the spring semester, but in the fall semester, I just added that slide in for the next lecture, for Lecture 7, which I'm not doing. I think you're going to start having Dr. Garcia next week? Yeah. So you'll start Lecture 7 with Dr. Garcia. So we've got a question here, which is, what would happen if I gave you this question? I said, and let's get rid of the restrictions at the moment. Suppose I told you I've got an array and I claim, I'm not sure, but I claim there might be an element that is a majority, meaning it occurs more than half the time. And I want you to find it. Now let's forget about constraints. If I just said, I've got an array, it's got an element that might occur more than half, and I want you to tell me if one exists, and if so, tell me what it is. Okay, so if we got rid of the restrictions, what would you think about doing this? How would you try to solve this problem? So think about that for a second. You can type into the chat window if you want. I think I'm about 5 seconds behind you, so not too big of a delay today. So one way we could do it is we could look at every element and look at every other element. So I could look at this 11 and say, okay, I'm looking at 11, how many other 11s do I see? Okay, I'm looking at a 13, how many other 13s do I see? I'm looking at a 99 from there to the end. How many 99s do I see? So I could do that with O of 1 memory if I took n squared time. So that would work. Okay, what about if I were to sort it? If I were to sort it, then I would get n log n time. I wouldn't need any extra memory, and then I would just have to go back through and look for the biggest chunk in a row of elements that are the same. Okay, well, we're saying if we got rid of the restrictions, how would you do it? So we're not going for the best solution yet. We're going for how would you do it if I didn't give you those restrictions? So if we compare one element to every other, then we get n squared time. If we sort it, we get n log n time, and then we just have to look for the biggest group in a row that are the same, and that would just take O of n. So we'd have n log n followed by O of n, which would give us n log n. Okay, if we want to find it in linear time with no extra memory, we're going to need loops, right? We're going to need multiple loops, exactly, because we are, in linear time, we are allowed to look at it more than once. So what we can do is we can look through and I'll say, okay, I've seen, let's see what I've most recently seen. I've seen an 11, and how many times have I seen it? I've seen it once. Then when I look at the 13, I say, well, that 13, you know what that 13 does? It's not an 11, so it cancels out that 11. I'm looking for how many of this thing have I seen that hasn't been canceled out by anything else. So I say, okay, I saw a 13 canceled out the 11. Oh, wait, I've seen a 99, and I've seen it once. Oh, wait, I saw a 12. That 12 canceled out that 99. Then I saw a 99. I've seen it once. Oh, wait, the 10 canceled it out. I've seen a 99. I saw another 99. I saw a third 99. So when I get to the end, if this count is greater than 0, I might have a majority element. I might not. We'll look at a counterexample in just a second. So now I've got I think 99 might be a majority element. What I've got to do is go back through the array one more time and count the number of times that 99 actually occurs, not how many times it's not canceled out by someone else. So the first pass is how many times do we see it that no one else canceled it out. Second pass is how many times did it really appear. Let's see. No, I've got 5 99s and 4 other values, so I really do have a majority. So what if we had something like this. What if I had 1, 2, 1, 2, 1, 2, 3? I get a 1, the 2 cancels out the 1 and the 2 cancel out, 1 and 2 cancel out. Ooh, look, I've seen a 3. That's why we have to go through it again to count the number of times that 3 actually occurred. If 99 wasn't the last one, that would be okay. What if I had something like this? Just get rid of this. What if I had like 99, 99, whoops, I'm kind of mashing them together there. What if I had 99, 99, 10, 11, 99, 99, 99, 12, 13. I'd say, okay, I got 2 99s, which are canceled out, 1, 2, 3 99s, only which 2 are canceled out. I'm still left with 99 occurs once. Let's go back and count it. So you can go play what ifs with this, etc. But this is called Moore's. The most common name is Moore's voting algorithm. And it's a good one to know for interviews. Now the bottom one says, what if I did the same problem, but I told you that's why you need the second pass through there, Charlie. You've got to make sure that it really is a majority. So the first pass gives you a potential majority. Second pass tells you if it's really a majority or just happened to be the one value that was never canceled out. Okay, so if I said it was n over 3, or what if I said it was n over 4, or n over 5, or what if I said it was n over k times? Well, we can't quite do this. We've got to restrict the we got to lower the constraints a little bit. So if we lower the constraints a little bit, what we've got to do is we've got to say that the average time is O of n, and the memory is O of k. So whatever k is, we're going to need that much memory. And we might get a time worse than this, but it might be, on average, it'll be as good as O of n time. So this one has a slightly different name. This is called Misra Grease. And to solve this one, with this average time and O of k memory, we need a hash table. And is it O of n? Or it might be, I might be off a little bit. It might be O of n times k. It might be O of n times k time. Yeah, it's O of n times k time. So that's that one, though. We can't really do Mr. Grease until we get hash tables. So we're gonna learn hash tables right after the midterm. All right, so you can play with that one a little bit later. All right, here's a question. Simple seeming question, super simple question. I've got a 4-line program. I want to know what line 5 does. So I've got an array of doubles. I've got an integer index. And up till there, we're fine. Lines 1 and 2 are fine. 3 is blank. 4 is fine. So 4 just says print out a sub I. Okay, I would expect to see for that, I would expect to see 2.2 displayed. Now, the second one, the second C outline, line 5, what does it do? Does line 5 give me a compiler error? Does it give me a runtime error? Does it work? Work meaning like no seg fault, no complaints if I run it with Valgrind. So what does this do? I was given this question by Igor Markov, and as soon as he said it, I was like, my first knee-jerk reaction was, that's not even going to compile. And then I thought, wait a minute, he wouldn't be asking me this question if it was that easy. So it's got to compile. And then I went, oh, it's so easy. It has to do with how pointers work. So there's what that program does. It outputs 2.2 and it outputs 2.2 because A sub I is the same as dereference of A plus I. And I sub A is the dereference of the integer I plus the pointer a. Remember, the name of an array is a const pointer. It's a pointer that can't be changed to point to anyone else. So it just reduces this to pointer arithmetic. Yeah, it's a terrible thing to do. Yes, you're right. It's a terrible thing to write code this way. It's not understandable, but it is good to understand, to remember how pointers work. And we showed you this today because we're going to be doing a bunch with pointers today. If you haven't heard me say it before, you don't need pointers in Project 1. You're going to have enough pointers in Project 2, trust me on that one. And in Project 1, you could solve this particular Project 1 with pointers. We have other Project 1s where pointers just will not work at all. But in this one, pointers would work, but you've got to be careful with the size of them because a pointer is 8 bytes, and there's something smaller I could use instead of a pointer. I could use an index, and I could use a 4-byte integer. Okay, so we do need to understand how C arrays work, including multi-dimensional arrays. We're going to talk a bit about that today. How pointers work, including function pointers. Actually, that slide's outdated. We don't do function pointers anymore. We're going to use function objects because that's C++. Function pointers is C, and we don't need it anymore. We've got functors, and next time we're going to teach you a little bit more about the STL, functors, and lambdas, actually. We need to know how C strings work. C strings meaning a pointer to a sequence of characters that ends with a \0. And these are great things to know because we'll use them for examples. They might come up in homeworks or labs. They might come up in interviews. They might come up in legacy code. Legacy code means code that already exists. So chances are when you get hired for a job, they're not going to say, "Oh, whew, good, we hired a programmer. You can start coding now, and we don't have a project yet. We just got an idea. Now we can start coding it." You might do that with a startup, but most companies that's not going to be the case. You're going to come in, and there's going to be 500,000 lines or 750,000 lines of code there, and it might be old code. It might have function pointers. It might have C strings. And you've got to deal with what's there. And you might start saying, hey, we've got to start, as we add new code, we've got to update it and make it better. But they usually are not big on rewriting 500,000 lines of code and hoping that you don't introduce new bugs that never existed before. However, for your projects, we want to avoid arrays. We want to use vector. Now, there is something in C++ called array. Array, I find, is not as useful because it's like a vector, but it can't grow. You have to declare the size up front. You have to know the size. If you pass it as a parameter, you've got to know the size. So I've actually never found a reason to use the array class. We should try to avoid pointers where possible. In Project 1, we can avoid pointers. In Project 2, there's one part of the project we can't avoid pointers. There's another part of the project that you might avoid pointers. It actually depends on which version of Project 2 it is. But part of Project 2, you're going to have to use pointers. We want to use, when possible, we want to use the STL containers, things like vector and dec. We want to use function objects or functors, things that overload operator parentheses. We want to use integer indices. Sometimes we want to use iterators to walk through a container. We want to use string objects. The very, very first time, nope, that's not Spencer, that's Yuki. So that cat you just heard, that's Yuki. She's a white Maine Coon. She's huge, and she's completely deaf. So I can't exactly call her over. So if I get a chance, I'll show you if she comes near me. Okay, so string objects. Like in Project 1, when I first created the Letterman project, I said, oh, got to write a solution. And I started writing a solution. I was like, ooh, I'm going to make a char pointer, and I'm going to do a new for every word so that I have exactly the right number of bytes. A 4-character word will only occupy 5 bytes. Oh, wait. Come here. Okay, we do have an appearance by the cat. So there's Yuki. She's not big on being held. She might sit still for just a minute. Yep, Yuki for snow is exactly right because she's a white Maine Coon and she's a big kitty. So, okay. Oof. She's not big on being held. So, show cat, successful. So anyway, I started writing project 1. And I started saying, hey, I'm going to do a char pointer for every string is going to be exactly the same the right number of bytes, like a 4-letter word will occupy 5 bytes. And then I said, no students are going to do it that way. That's going to make the amount of space just impossible for most students to meet because students are going to use string objects for project 1. So that's how I wrote the real solution for project 1 that your timing and memory is based on, because it was the straightforward way we would expect a student to write it, and that's what we base our timings on, is a straightforward project that we expect students to be able to produce. Okay, so we've got a little bit of review here of, I've got Yuki fur on my face. I've got an example here of using an array of characters. So it started out with EECS. It started out with an A here, and then I overwrote the A with an E. I can make a copy of a character. I can make a char pointer equal to the name of the array, and I can move the pointer around. I can say the pointer equals AR plus 1, or I could say pointer plus plus. I can move PTR to point to different places in memory, but AR can't move. AR is AR is a pointer that points there in memory. Where is there? Well, I didn't do a new, so it's not on the heap. The array AR is actually part of what's called the data segment. It's part of the executable image on disk, and it gets loaded into memory, and the program, once it's loaded into memory, it knows where to find it. What I'm saying is, on project 1, you could use less memory if you use C strings, but you would probably go over on time, because C strings are not as fast as string objects. Because C strings, every time you want to know, hey, are these words the same length? You got to count the number of characters in both words. So you'd probably go way under on memory and way over on time. So I didn't write it that way. I wrote it a straightforward way. Now, let's look at fixed size arrays. So fixed size arrays in memory, I've got a one-dimensional array here, int A1D, and I've got on the right, I've got int A2D. So in the first one, I created it and I showed you where each index is in memory. So I've got the rows and the columns for the second one. So the first one just has an index, and the value and the index are basically the same. Now in the second one, I declared it to be a two-dimensional array of 3 rows. This is the rows, and this is the number of columns. Now I know the 3 by 3 doesn't quite show that well. I suppose I could extend this to a 3 by 4, but then I'd need 12 for the first one, and that wouldn't fit very well. I suppose I could do a 3 by 2 or 2 by 3. That would work just as well. But we've got trust me on this, when I say A2D, the first square brackets is the number of rows and then the number of columns. Now, actually, what happens in memory is they both look like that in memory. In memory, they're both laid out like that because my memory chips are one-dimensional. My memory chips have one address. My memory chips don't have a row and a column. They've got an address. And so the elements of my array are always laid out like that, whether it's a 1D or a 2D or even a 3D would be laid out in memory one element after another the same way a one-dimensional array would be. Now I can create a one-dimensional array and treat it as if it's two-dimensional, or create a two-dimensional and treat it as if it's one-dimensional, because I've got formulas that can go back and forth. If I've got an index, I can turn an index into a row and a column number using those formulas. And if I've got a row and column number, I can turn it, so that's my row and my column number. I also need, to do these formulas, I need the number of columns. I need this number. That number is important to the math. So when I say num columns, I'm talking about, backwards. When I'm talking about the number of columns, I'm talking about this value right there is the number of columns. So that's always the number of columns for these formulas. We have to know it to be able to do the math. So I can convert from a row number and a column number into a one-dimensional index using that formula. So I could actually treat a 1D as a 2D, treat a 2D as a 1D. And sometimes people try that, and they'll do it sometimes with vectors. Like they'll say, hey, I'm not going to create a 2D vector, I'll create a 1D vector and treat it as if it's 2D. And yes, sometimes that uses a bit less memory, but it makes you do the math instead of the compiler do the math and the STL do the math. So I tend to just do it whichever way represents the data the best. Now, I've got another example here with the fixed size 2D arrays. I made some named constants. So I made some named constants, and then I created an array of that number of rows and columns. And then I create a value, starts out at 0, and then I ran through some loops for every row R, for every column C, run through and set array sub R sub C equal to the value, and increment the value. So it runs through, it says 0, increment it, 1, increment 2, increment, da da da. When I'm all done, value has 9 in it because I store 8. Notice this is a post increment. I store the value 8, then I increment the variable val. Whoops, I mistyped that. The variable val gets incremented to 9, but then the loop is over. For a fixed size array, I can declare it and initialize it at the same time. Now here in this inset box here, I could have put rows and columns in there. It just didn't quite fit in the slide. So you can then put the curly braces to say, here's the initialization of that array, and the inner curly braces are to help me read it, to indicate where a row begins and ends, to make it easier for me to read the big block of initialization here. Now, the nice thing about this version is it doesn't use pointers. It's safer. It's safer because I don't have to remember to do a delete when I'm done with it. However, the size of this 2D array is set when it's created. So either in line 2 here or in this line here, the size of the array is set. It's when it's created or in the right-hand box when it's initialized. So the creation of the array sets the size and it's fixed. Now it does use less memory than if we did a 2D version with pointers. We're going to look at that in the next slide. Now in G++, there's an extension. In G++, we could do something like this. Let me get rid of all the markings on here. In G++, I could get rid of the const, I could get rid of the equals 3 and the equals 3, and I could put a line of code in there that says cin goes into rows and it goes into columns. And then line 2 would work. Now that's G++ only. Visual Studio doesn't allow it. The Clang or LLVM compiler does not allow it. So you don't want to get into the habit of using this. It's compiler dependent, and it shows that you don't, like if you pulled this out in an interview, this would show me that you know one thing about one compiler, but you don't know that it's not portable. So we try to avoid things like that that are compiler specific. So I want you to know that it exists, but I want you to not use it. Okay, what about if we use pointers? Now, like I said, we could have done a one-dimensional block of memory of size 9 and then done all of the translation from row and column to index ourselves, but I didn't want to do that. I wanted to do it all with pointers. So what I did here is I said I've got a number of rows and columns. I didn't use capitals here. I tend to reserve all capitals for constants. So I've got some variables I read in, and granted, it would probably be nice if I did a cout there to tell them, you know, I want you to tell me how many rows and columns you want this array to be, but I didn't have quite enough room in the slide for a big prompt like that. So I read the number of rows and columns, and then we do a new. We're going to break down this syntax. So we're going to do an int pointer array, ARR, equals new int pointer rows. Okay, this is two-dimensional. Let's go back to one-dimensional and look at the syntax. So if I want to do one-dimensional, I could say like int pointer a1d is equal to new int. And if I was doing it, I could say something like new int rows times columns, or whatever, however big I wanted to make it. So here, because I'm creating an array of integers, I have a pointer to integers. However, what I want to end up with in the 2D version is I'm going to do a new on each of these arrays. So each of these arrays is going to be newed. The result of each of those news is going to be a pointer to integers. So the outer one has to be pointers to integers. So I'm saying ARR is a thing that points to things which point to integers. So that's what we're saying there. This is a thing which points to other things which point to integers. So then I'd create, so line 4 here, let me get rid of a little bit of writing here. I want to change the color so I can demark this over here. Okay, so let's change color. So this right here is line 4. So that's line 4 creating that outer one. At the moment, it's not pointing to anything. Those are all elements 0, 1, and 2 of ARR don't exist. They are not initialized yet. So they don't actually point to anything. When we get to line 8, let's change colors here. Line 8 is where we create each of these. So that's line 8 does that, and we're inside of a loop. So inside the loop, line 8 creates one, line 8 creates another one, line 8 creates another one, and then we're done. And it creates them, and it sets this thing to point to it. So element 0 points to the first block, element 1 of ARR points to the second block, element 2 of ARR points to the third block. Now, once we're done with all that, when we get down to line 15, in line 15, I just treat it as a two-dimensional array. When I say ARR sub R, I'm referring to, this thing's getting really busy now, we're going to have to erase a bit to be able to see it. So now, when I get down to line 15, and I say ARR sub R starts out at 0, so when R is equal to 0, ARR sub R is talking about this pointer. And then when C is equal to 0, ARR sub R sub C is looking at that element right there. Well, the advantage of this one is we can get the size at runtime. So that's the advantage of this version. This version, I get the size at runtime. This version, the size is fixed at compile time. And we're going to talk about that in a minute. So that's all of the creating and filling it with values. So in the inset view over here on the right, let me erase this stuff again. So when we're looking at this stuff over here on the right, when I've got one of these boxes, the green, I think it is, the lower subscript 0 is the index within this row. And so the black one is the actual value that line 15 stored in. So line 15 stored the value 0, and it's at index 0 within this row. This is index 1, index 2, and then when we go to the next one, 3 is the value, but 0, 1, 2 is the index within this row. That's C, is those indices. And I don't have a green pen handy on my tablet, at least not recognizable to me as green anyway. Okay, so then we'll assume that we did everything we want to with this array. We've got some more code in here that does some like averages and medians and all kinds of stuff, and then maybe prints it out. But then when we're all done, we've got to go clean up. We've got to delete the memory that we knew. And we've got to destroy it in the opposite order that we created it. Now, not strictly opposite. I don't have to delete row 2 before row 1, but I have to delete the rows. I have to delete all the rows before I get rid of the whole thing. So I've got to delete each of the rows. If I delete ARR first, I've deleted the thing that points to the other things. If I delete ARR first, like if I move line 22 up before the loop, then the loop isn't safe because I don't really own those pointers anymore. So it might work, but it might not work. I know it works in this order all the time. Okay, so pros and cons of the fixed size arrays. So fixed meaning fixed at compile time. So fixed at compile time, it's allocated on the stack, not the heap, which means it's automatically deallocated when it goes out of scope, meaning like the function ends. If this was inside a main, it gets deallocated when main ends. If it was inside of another function, it goes away when the other function ends. The other nice thing is ARR sub I sub j, or sub row sub column, uses one memory operation. It has to go out to memory once. However, before it goes out to memory, it has to do the pointer arithmetic. It has to figure out, oh, you want this row, that column. That means you want index, 8. So it has to do the math first, but then it only goes out to memory once. And we'll look at the difference with the pointer in just a second. The downside is it doesn't work for a large n. And that n, how big of an n can I make before it gives a stack overflow, depends on the compiler and operating system. So that size is fixed at compile time, and also these fixed size arrays are difficult to pass as arguments to functions because we saw this last time where we did the stepwise linear, and we had to tell it, hey, I received an array, but I had to declare square brackets for the number of rows, square brackets n for the number of columns, and I had to know that number at compile time. Now, one thing we want to remember is we really want to avoid fixed length buffers for variable length input. This is how this is a 70%, it is an estimate from security people. This is an estimate of how many security breaches happen because someone created a fixed size array and accepted variable size data and maybe like goofed up the check that the size was big enough to hold that variable size input. Even when people do variable size arrays with the news, sometimes they mess it up. Now with the dynamic arrays, the upside is, one, it supports triangular arrays. If you've had linear algebra, you know what that means. If you haven't had linear algebra, all it means is that every rows could be different sizes. So if you've had linear algebra, you might know why it would be useful to have rows that are different sizes. The other nice thing is it allows us to swap rows around quickly. See, if I go back 3 slides, this one, if I want to flip the entire array top to bottom, I've got to swap around all the values. And yes, Charlie, you are exactly right. Heartbleed is a great example of that. Okay, so if I want to swap all these values top to bottom, I've got to swap all rows times column values have to get swapped. In this one, I have to just swap the number of rows pointers. I just have to swap this pointer with that one, and I'm done. I've swapped the whole array top to bottom. Okay, and the size can be changed at runtime. It's not fixed at runtime and decide how big it is. The downside is we have to remember to write that matching delete. One thing I like to do is when I write code, as soon as I start writing code, I'm going to clear out this stuff on here now. As soon as I write this new, I go down and write that delete. And as soon as I write this loop, I write that loop. just to make sure that it doesn't get forgotten. Now, you might ask, why did I put this size t outside of the for loop? This one right here, I put that outside of the for loop just because I was limited. I ran out of columns, and I didn't want the for loop to be 2 lines, so I created the variable on a separate line. So this one, when I write news, I always write matching deletes so I don't forget them. Now, the other thing is the ARR sub I sub j is slower than with a built-in array. It's slower because it has more than one memory access. When I say, oops, forgot to go back one more. When I say here ARR sub row sub column, what happens is, let's say R is equal to 1 and C is equal to 2. I have to go to ARR and go to index 1 of ARR. I have to look at this pointer and follow the pointer. Then I've got to go over to this section in memory. So I have to access this pointer in memory, this pointer of saying where do I point to, and then I've got to access that value in memory. So I've got to go out to the memory chip twice potentially. Now, beyond this, I don't really even have to do this. I can use vector, or I can use vector containing vectors. Now, you don't need that for project 1. However, because we only did a 1-dimensional project 1, we're going to do a 2-dimensional project 2, so you're going to need to know how to have to do a vector containing vectors for project 2. Now, there's a bunch of off by 1 errors here. This is sort of more basic 280 type stuff. I would take a look at this slide and realize why each one is wrong, but I don't want to spend any time on that one. Range-based for loops. So you probably learned about the range-based for loop. It has a couple different names. It's called the range-based for loop. Some people call it the for each loop. Some people call it the enhanced for loop. So there's a couple different names of this. So range-based for loop is as good a name as any. For each is good. So in here, I wrote the classic version of I want to double all the values. I've got an index. I take the index. I multiply the value I find times 2, and I store it back into itself. So remember, line 6 here is the same as saying my array, I'm just going to write it shorter, my array sub I is equal to my array sub I times 2. So it's a shorter way of writing that. Now, in the second version, in the range-based for loop, I did something you might not have seen before. In the second version, I made a reference. And I made a reference because I want to double the original array. If I get rid of the ampersand here, I make a copy of 1, and then I double it, and it becomes 2. The copy becomes 2, but the original stays 1. So if I get rid of the ampersand, the array doesn't change. But with the reference in that line, now the values in the array actually get doubled. Now you might say, wait a minute, I thought you could only create a reference once. Well, this reference gets recreated every time the for loop runs. So every time this for loop runs, the reference is recreated to be a reference to a new element of the array. If all I wanted to do was output them, like if I wanted to do another loop, I could say like for, I'm going to use auto here, auto item, colon my array, and I wanted to do like cout, less than item, less than, let's put a backslash n in there. With that, I don't need a reference. Since I don't need a reference, I make a copy of an integer, I display the integer, but I'm not changing them. So this is a place where I don't need a reference. So I need a reference, if I'm going to change it, got to have a reference. This is basically same rules that are in the Canvas Files Resources Optimization tips for passing variables. So if you're going to modify it, got to have a reference. If it's a small thing like an integer or a character, or actually I should say else if. So if I'm going to modify it, got to have a reference. Else, if it's a small type, like a built-in type like integer or char or double, use it by variable. Else, const reference. So that else would mean like it is an object, but I don't need to modify it. So if I put const reference in this for loop, as I said, const reference, it would tell me line 10 is invalid. I made a reference. I promise not to change what it refers to, but line 10 changes it. I would break that. So we could put const in this version, but we don't need to because we're making copies. The which is faster depends upon the container, but usually the enhanced for loop is faster. Okay, we've got an example here of strings and arrays. And 1 second, I've answered a bunch of questions because I'm not too far behind. I'll be right back. We don't seem, maybe I'll just say on Slack, I don't seem to have anybody from the 281 staff, at least not any names. Oh, wait. Danielle is actually on staff. Okay, we do have at least one person here. Good. Okay, so in this example, we've got a simple program. Ooh, I just realized there's a typo in this slide. Get rid of the const there. Xcode likes to put const in there, but for our projects, when we use get-opt long, const is bad because some compilers won't compile if you put const there, because get-opt long doesn't promise to not change things. Okay, so we've got a simple example where we're string copying out of argv of 1. However, this code is full of bugs. One thing that could happen is, what if they didn't put anything on the command line? Then argv of 1 shouldn't even exist. Like, if they didn't put anything on the command line, argc should be 1, because argv of 0 is always the name of the running program. And yeah, I just didn't recognize your name, Danielle. We've got so many new staff members, I forget everyone that's new. Okay, so we've got so if they put nothing on the command line, argc is 1, argv of 0 is the only one that exists, and argv of 1 is either an invalid access, a null pointer, something bad's going to happen because I didn't check to see if there was something on the command line. The other thing that could go wrong is they could put something on the command line. So argc is 2 or greater. It could be 3 or 4 or 5. If they've got, no matter how many parameters, if argc is greater than 1, I can look at argv of 1, but I create a fixed array of size 20, which means my string has a maximum upper limit on it. My string on the command line could be at most 19 characters, plus string copy puts a \0 in there. 19 characters plus a \0 is the biggest that'll fit. So a little bit better version would be make a string object, check argc first to make sure it's valid, and then copy from argv sub 1 over to name. And this string has a convert assignment. It says, hey, you want to take a char pointer and assign it to a string object? I'll go copy the characters one at a time and put them in there. So we got rid of the bugs in that one by checking argc and using a string object. Now, a better way even than line 8 would be to use get-opt long. And we do use string objects, like we showed you that in the project 0, and you're probably using it for project 1 for like the begin word, end word, output mode are all strings. Now, when we do news and deletes, so new, we use new when we want to create one object, and it calls the default constructor to create that object. Now, these notes here apply to both of those. I just didn't want to repeat it. So whichever new we're doing, there's actually no constructor to call if we've got basic types like int or double, And if, and really this one should be indented another level below that, if they are default types, or sorry, if they are basic types or primitive types like int or double, char, bool, etc., there's no constructor and there's no initialization if they are primitive types. If they are classes, then the constructor runs and the constructor is responsible for initializing everything. Now, when we do a delete, we're still on new. So we've got new to create one, new square brackets to say, here's how many I want you to create. And the value inside of new square brackets obviously has to be an integral type. We can't create 2.5 strings. So we create an integer number of copies, and that number can be known at runtime. It could be known at compile time, would be fine, but it has to be known by runtime. Now when we do a delete, we've got either delete to delete one object or delete square brackets to delete a bunch of objects or a bunch of primitive values. If it's primitive types like int, double, char, etc., there's no destructor called. We have to remember we only use delete on things that were created via new. We don't use delete square brackets if we did a new without square brackets. We don't do any type of delete on something that wasn't new. Like if I just say, hey, I've got int x, and I've got an int pointer p is equal to the address of x. If I do delete p, that's invalid because p does not point to the result of a new. So we can only delete things that were allocated with new. We delete square brackets, things allocated with new square brackets. Now, one thing that C++ does that's nice for us is when we do a new, we've got to tell it the size. How big is it? But when we do a delete square brackets, we don't have to tell it the size. We don't have to put the size in there, which is good because it removes another potential source of errors. But how does it know how much memory to get rid of? When we do a delete square brackets, how does it know to do this? How does it know how much memory to get rid of? What it actually does behind the scenes is if I do something like, I'm going to have to get rid of my marks on here, make up a little room here. If I do a double pointer PD for pointer to double equals new double of, let's say, 8. What happens is this thing returns a pointer to something that looks like this. This is actually my memory, but what's here, there's an 8 here, and this, I ran out of room there, there's 8 elements there. But it gives me a pointer to the first element of the memory that it's supposed to put doubles in. This 8, actually, really, there's probably not an 8 there. There's probably a 72 here. And the reason, let me erase that a little bit, what's back one step is the value 72 because that's how many bytes are occupied by the whole thing. So there's 8 doubles times 8 bytes each, that's 64. The size itself is 8 bytes, so there's 72 bytes that are actually allocated. So when you do a delete square brackets, what it does is it looks here, the pointer you gave it, it steps back 1 and gets rid of that many bytes. So if we know all of that, why are there 2 versions of delete? Why not just have one version of delete that figures it out? Because of the size. When I do a new actually returns a pointer to the memory that's allocated. There's no size. There's no extra storage for the number of bytes. If I do a new, like if I do a new char, I get a pointer that points to 1 byte of memory. And when I do a delete, and I say, hey, delete this thing, it says, well, I know you gave me a character pointer. Character pointers are 1 byte of storage. I get rid of 1 byte. So it makes it simpler and less memory usage to have 2 versions. New square brackets has to record the size. Delete square brackets has to look at the size. But new and delete don't have to store the size. They don't have to look at the size. Okay, so now some cooler stuff. So suppose I'm going to make a container. A container is an object that contains multiple copies of data items, such as a container containing ints or doubles or string objects or whatever. We're going to make a container because we want to allow some control and protection over the objects stored in the container. Like a stack would be a container object. The stack's control and protection is you can only access the top. You can add at the top, you can look at the top, you can pop from the top, and you can ask me about the size and stuff like that, but you can't go down in 3 elements and delete something from the middle of my stack. I don't allow that to happen. I have protected my internal data. Now, with classes, we can allow whatever behavior we want. So we could allow like a copy constructor or an operator equals. We could provide sorting of the internal data if we wanted to do that. We could allow editing of internal data or not. We could allow them maybe to only edit the top. So we decide what they can do, where they're allowed to do it inside of our container. And we use these containers when we create more complex data structures. So in Project 1, you're already doing this. If you've got strings inside a struct, inside a vector, you've got 3 levels deep of data structures. You've got a vector of structs containing strings, and oh, well, what does the string contain? String contains characters and pointers and other stuff. So it's really 4 levels deep already. Because I can say something like, and if I put that dictionary inside of a class, I'm 5 levels deep. I've got an object contains a vector, vector contains structs, struct contains strings, strings contains characters. I'm 5 levels deep, just in Project 1. So that's how we make more complex data structures, is by putting containers inside of containers. We can do this to search through data. We can use it to organize data, like we're doing in Project 1, where we've got the vector of the dictionary that we think of in memory, and we've got the search container that tells us where to look within the dictionary. And something like a database, like SQL. A SQL database, SQL database, can be viewed as a very fancy container that maintains most of its data out on the hard drive. So examples of container classes, we're already using things like vector and dec. We've talked about stack and queue and linked list. We're going to talk after the midterm, we're going to talk about maps and unordered maps. These are all parts of the STL, Standard Template Library. And our next lecture, next Tuesday, is going to be more about the STL. So, most data structures in EECS 281 are containers. And today, what we're going to do is we're going to use array-based containers as an example of a type of container. So, things I would like to do with a container. Okay, I'd like to be able to construct them and destruct them. If I'm going to have a destructor, that probably means my constructor did a new, which means if I've got a constructor and a destructor especially, I should probably also have a copy constructor. I should probably have an overloaded operator equals. So I should probably do those also. I want to also be able to add elements and remove elements, common things to do. Get an element from the container. Maybe ask the container its size. Oh wait, I did. I guess over here copy could be both of those. So we could say that when I said copy over there, I didn't forget, I just didn't read far enough. So copy could mean copy constructor, operator equals. I might want to assign an element. So I might want to add an element, and then later on I might want to change the value in an element. And what other things might we, whoops, it's trying to get me to draw with my finger, what other things might we want to do with a container? So if you were making a container, what would you like to be able to do with your container? Maybe you'd like to be able to display the contents. Like, I'd like to be able to say cout less than dict, D-I-C-T, the name of my dictionary. I'd like to say cout less than dictionary and have the whole contents go to the screen. That would be nice. Vectors don't support that. So I'd have to have a container that supports it. Then my structure inside the dictionary would have to support it also. So I could make, if I'm making containers, I could make my own other operations like an output operator. Whoops, now it's got me drawn with my finger again. Okay, now when we create a container, I've got to decide up front, what kind of access am I going to allow to my container? I could allow sequential access. You've got to look at the fifth item. You've got to look at the 4 that come before it. I could allow random access. I could allow both. It depends on what I want to accomplish with this container. Something like a deck allows both. A vector allows both. So we're using a deck as if it's got, push front, push back, pop back. But remember, a deck has operator square brackets also. So vector and deck allow both of these. Stack doesn't allow iteration at all. Stack allows access at one end. Queue allows push at one end, pop at the other. So we're gonna look at those soon, Andrew. We're gonna show how we could do that. We can't overload it for everything, but we'll show you the right and wrong way to do it. If it's not coming up today, it'll be next time. Okay, so we've got these different things that we could do to allow the access to the data in whichever way we want. Now, pointers. Remember I said it's good to know how pointers work. I've got a version here of copying from the source array to the destination array without using pointers, and I've got a version that does use pointers. Now, if we can write it without pointers, why would we do it with pointers? A couple of reasons. One is the second version is faster. Second version is faster. It's not as easy to read, but it's faster. Another reason, if I change from arrays to something like a linked list, the second version, if I rewrite it with iterators instead of pointers, iterators are just a generalization of pointers, I can do the iterator version, whether it's a vector or a deck or a linked list. The square brackets version would only work for a vector or a deck. Square brackets doesn't work with linked lists. So the second version is more generic, and it's actually faster. Now, do we expect you to use iterators on the projects? No, we didn't write our version using iterators. We expect you to write the straightforward version. So given a vector, I would expect you to write the top version with indices. But you can do the iterator version using iterators over a vector. We wouldn't want to use pointers with a vector because a vector has private data. We should use the iterators to walk through it. Now, the syntax here in this assignment is critical. So this says, I want to assign to something. Okay, I have to know what I'm assigning before I can assign it. So it says, dereference the source pointer. So dereference the source pointer is the value I'm going to copy, and then I should draw it your way. So dereference the source pointer is what I'm going to copy. Dereference the destination pointer is where I'm going to put it. Then I can do the assignment. The value gets copied, and then because they're both post increments, the increments happen last, after the copying happens. Which increment happens first? Don't know, don't care. It might even be one of those that the compiler makers are allowed to decide. But I'm never going to count on what order those increments happen in. I'm just going to know they both happen. and they happen after the assignment. If I try to put parentheses in this to make it clearer, it makes it wrong. So if I were to write it this way, so if I just replace line 11, I want to say, hey, I want to say dereference of destination pointer plus plus equals the dereference of the source pointer plus plus, a couple of things happen. I look at the source pointer and I copy the value, so that would copy the 3 out of here. It would put a 3 in the destination. Then it would increment this 3 to become 4. It would increment that 3 to become 4 because the plus plus is now applying to the value, not to the pointer. And so then I'd change this to 5 and 5. Or actually, I'd change this. I'd overwrite this with a 4 because I copied the 4. Then I'd change them to 5 each. Then I'd overwrite this with 5. Then I'd change them each into 6. And it would be an infinite loop because my pointer never moves. I never reach the end of the source. It's an infinite loop. So it's critical that we write it in the way it's said there. This right here is so ubiquitous, which is a fancy English word for it occurs everywhere. There's a classic operating systems textbook that has that loop on the cover of the operating systems book because it's the way that low-level stuff gets written. Now, last thing is the while loop. Why is it source pointer not equal to source array plus size? Okay, so if I'm looking in memory, src array points to somewhere which has 4 elements, 3, 5, 6, 1, and then I make a source pointer. Source pointer points here. I copy it and then I move it over. Then I copy it and I move it over, copy it and move it over, copy it and move it over to the end. If source array is here, source array, let's change colors, source array plus size, whoops, S-I-Z-E, source array plus size points to here, just off the end. Would a less than work here? If I change that to a less than, does it work? Yes, it works. With arrays and with vectors, it works. With a linked list, it won't even compile. With a deck, it might work, it might not. But not equals always works. So less than works with some containers, not equals works with others. Now you're going to hear me say this and say it in the air a lot because, well, I'm Italian, so I draw things in the air. When we talk about containers in C++ and we talk about iterators, we're going to have basically the begin iterator is inclusive, the end iterator is exclusive. So I'm going to show you this, like I'm going to draw it this way. I've got square brackets beginning, exclusive ending. Trying to get the right camera angle here. So inclusive beginning, exclusive ending. We're going to see that a lot. That's how the STL expects iterators to be. Inclusive beginning, exclusive ending. And it does a while my iterator is not equal to the end, I can keep going. And when it is equal to the end, the loop stops. Okay, what am I going to put in my container? Okay, what am I going to put in my container? I could put whatever type I want to, right? If I'm going to store characters, I could put characters in my container. Now, my data ownership is the container owns it. And I'm talking about not just like a character variable inside my container, but let's say my container contained a block of dynamic memory holding chars. Then I own that. I own that block of memory which contains some number of characters. I am the owner of it. I'm the only one allowed to edit it. I'm the only one allowed to delete it. Now the downside to this is if I make a container containing copies of large objects take time to copy. This is actually the most common thing to do. So when we make a container, we'll often make like a container that contains strings, or a container that contains like a vector of strings, or a deck of integers. Now I could, inside my container, I could put pointers inside my container. So I could have like, inside my container, I could have a vector of char pointers. So I could have so the first one here is internally I have a vector of char. Here, internally, I have a vector of char pointers. Now then the question is, who owns what? The container class owns the vector, but who owns the things that vector points to? Well, you could claim that the container owns it, or you might claim someone else owns it. You've got to decide. It's a little bit unsafe to use because if I have a pointer to somewhere in memory and someone else deletes it, then my container is invalid now. My container has a vector of char pointers, and one of my char pointers has been deleted, and I shouldn't be looking there anymore. So it's a little bit unsafe. It is sometimes done if I'm going to have shared data. Like if I'm going to have a container of stuff and it's big, I might make another container that has pointers to the original container. So that way I don't make copies of those big pieces of data, I share the data. I've just got to be careful that if the original container starts getting rid of stuff, I don't look at the second container. Okay, third thing I could say is internally, I have a vector of references to characters. Doesn't compile. So you can't really do this. You can try it. There's a little bit of things you can get along this route, but mostly you'll get compiler errors and it won't work. And it's dangerous to do it. Even if you get it to work, you can initialize references, but you can't change the references. If you try to change the references, you change the original data. So it's a big hole of a big pit of compiler errors and runtime errors if you try to put references inside of a container. Like if you just say vector of char reference, won't compile. Now, what do I want to get out of it? When I say, hey, I want to give you access to what's in my container. Well, let's assume that we went this route, the most common route. So the bottom here is based on the first column. So if my container stores something like internally, so internally I've got a vector of char. So internally I've got a vector of char, but I'm only going to let you access it in certain ways. Like you give me an index and I give you back the character that goes with that index. That would work. The downside of that is if these aren't characters, if it's a vector of big objects, then the get element would have to return a copy of a big object. All right, what if I give you, so I've got a vector of chars, what if I give you a pointer into the middle of my vector? Well, then that could be unsafe because you might use that pointer in bad ways. You might modify that char pointer and put a \0 there. And I think I've got a vector of char that represents a 20 character string, but there's a \0 at index 2. So it would allow you to change it in ways that I might not want to happen. It would also allow you to like increment that pointer and look at somewhere else in memory that might be invalid. If you increment the pointer past the end of my internal vector, bad things could happen. All right, what if I gave you a reference to the thing inside my vector? That's actually a pretty good choice. And we'll do two things here. We'll make two versions of this. One that returns a reference and another that returns a const reference. Or maybe I'll only do the const ref version and I'll put the word const out there in front of that const char reference. So maybe I'll only have const reference to say, hey, here it is, you can look at it, but you can't change it. So we could do either reference, or we could do const reference, or we could overload it to provide both. And that's actually a pretty good choice, and that's what the STL tends to do. The STL will have things like reference, like if you ask for like v sub I, like I've got, or dictionary. If I say dictionary sub I, the square brackets operator of the vector returns a reference. Okay, memory ownership. This is a little bit of 280 review. Why don't we want to have two objects? So array is the class that we're going to write to part of. So if I make a class called array, I don't want two objects of my class pointing to the same block of dynamic memory. If I modify B, A looks like it magically changed even though we didn't change A. If I delete A and I try to access B, I'm accessing memory that nobody owns anymore. If I later decide to delete B, we try to delete that block of memory all over again, and then we are guaranteed to get a runtime error of an invalid double delete. We're deleting something that's already been deleted. So bad things if we've got two classes that have ownership of the same object. So we want to, when we do constructor, so we're talking now about constructors that do a new. If my constructor does a new, then my copy constructor and assignment, I could either create duplicate objects or I could create duplicate pointers to the same objects. I could have multiple containers pointing to the same thing. And this one is usually, this is bad. This is usually a bad thing to do. If we're really careful, we might do it. Like I said, we might have a master copy of the data that we don't change and we don't make copies of, and I've got another container that points into it. And if I'm really careful and make sure I get rid of the one that points to the objects, before I get rid of the objects, I might be able to do that. But we got to be really careful if we do that. But when we're talking a container, if I'm making a container where my container does news, this is definitely bad. If my container does news, I should have a copy constructor and an operator equals. If I don't write them, I get duplicate pointers. And no, that's not desirable. That's what we've got here, is if I don't write a copy constructor, I get two objects pointing to the same block of dynamic memory. Now, with ownership, one thing I could say is every object is owned by the container, and that container that owns it is the one responsible for deleting it. The other safe way to do things might be to have no ownership. I've got to have someone watching things, though, and deleting things that are no longer used or no longer can be accessed. Once there's nothing referring to something that got newed, then it can be deleted. Java does this by default. Java has automatic garbage collection, and it runs in the background. But Java doesn't have destructors because there is no guarantee that memory that you newed will get deleted before your program ends. The memory could get deleted after your program is done running. So that's why Java doesn't have destructors. Now in C++, there's a library called smart pointers that you're not allowed to use. If you've gotten a compiler message on the autograder that you're using unique pointer and you're losing 90% of your points are being deducted, that's what happened. You included something that included unique pointers, and you're not allowed to use unique pointers. You're not allowed to use smart pointers. My staff member a few years ago argued for this, said, oh, no, everybody knows pointers by now. They can use smart pointers in 281. I went to Dave Kieris, the 381 instructor professor, and asked him, and he was like, no offense to you, but students come out of 281 and they still don't know pointers as well as they should. So no, don't show them smart pointers in 281. It's a bad idea. Make them get better at pointers. Okay, so we want to have some sort of privacy and safety with our pointers. We want to make sure that we don't have two objects pointing to the same block of memory. We want to make sure we don't get a double destruction. We do want to make sure we do have a destructor to delete memory so that we don't have memory leaks. And when you write things, it is a little bit of extra safety to say, hey, I'm not just going to delete, I'm going to delete and set it to null pointer after I delete it, just as an added layer of safety, because then if I try to follow the pointer and dereference it, I get a seg fault immediately. Whereas if I don't set it equal to null pointer and I look at it, it might work. And one time I run the program, it might work, and another time I run the program, it might not work because I deleted this block of memory, somebody else did a new in the same place, and then I try to look at it, and bad things happen. And if I try to do a delete on, like if this one on the example on the left, if I added another line down here, delete pointer, that's what this note is saying. If I try to delete something that is a null pointer, that's okay. There's no compiler message, there's no runtime error for that. If you delete something that is a null pointer, it's just a do nothing operation. So what's wrong with memory leaks? You say, hey, when the program exits, the operating system is going to clean up that memory anyway, and that's true on modern operating systems. On older operating systems, it wasn't true. I used to play a game that I would play for a while, and eventually I'd have to, after 2 hours of playing my game, I'd have to save it, exit, and restart it because I knew if I played for another hour, it was going to crash with an out-of-memory error because somebody goofed up the code and was allocating stuff and never deallocating it. And I actually had, with an even earlier operating system, I had to reboot my computer because the game was leaking memory and the operating system didn't clean it up. Also, you say, well, nobody uses Windows 95 anymore. Mostly true. There's a few computers around the world that have Windows 95, but what about if we're in an embedded system? What if every time you changed radio stations in your Tesla, it forgot to do a delete? And then you're driving down the road and Tesla says, oh, out of memory error, please pull over and reboot car. That would be terrible. Or your refrigerator. What if your refrigerator just stopped working because you opened the door so many times that the sensor for the door has been open, lost memory every time you open the door, and your refrigerator crashed and you lost all your food? So embedded systems, we can't count on this. If you're writing code in a cell phone app, sure, it's going to clean up memory when the app ends. But if you're writing stuff for the cell phone operating system, people often don't reboot their phones until it's time for an OS upgrade. So we don't want to write code this way, even if we're not in an embedded system. Even if we write a little demo program that shows that something exists, and then our boss gives it to someone else, and that person sticks it as part of our bigger system. So mine was a proof of concept. Someone else took my code and included it in the big system because my proof of concept works, and they didn't notice that my proof of concept didn't delete memory. Now our big system leaks memory. So we always want to make sure we don't leak memory, because as it gets used in a bigger system, an embedded system, etc., it could have more problems. So we're going to start creating an array class here. Now our array class is a little bit limited. We're going to be allowed to create an array of a certain size, which is fixed at runtime, but it doesn't grow. It doesn't have a pushback. If we wanted to do that, we could. It would just take more and more slides of this stuff. So by default, if I don't say otherwise, this is private. The only difference between a struct and a class is the default access method, or the default access specifier. If you don't say otherwise, stuff in a class is private. If you don't say otherwise, classes in a struct is public. So I've got some private data. I've got my length and my pointer to the internal memory. It starts out as a null pointer. Then in my constructor, the constructor says, I'm passed a length in, and then the constructor says initializer. This, you're going to have to get used to seeing this. This is called the unified initialization syntax, or uniform initialization syntax. If you replace those curly braces with parentheses, it still compiles. It just shows that you're a little out of date on your C++ isms. So you're supposed to use curly braces for initialization. The colon here says we're doing initialization. These are the member variables, and they have to be listed in the same order. So length must be initialized before data. So it says initialize length, make a copy of whatever was passed in as len, and then initialize data, the pointer, by calling new double on length. And I could have said length here, or I could have said len. It doesn't matter which. I based it on my member variable. And that's why there's a rule about order of initialization, is that I want to make sure that I initialize them in the order they're going to be used. And therefore I should declare them in the order they're going to be used. So since I've got a constructor that does a new, I immediately wrote my destructor. Destructor deletes the data and sets the data equal to a null pointer. Line 10 is kind of optional because I know this is a destructor and I know the destructor is done, but if I were to copy this to another function that cleared the data or deallocated or something, putting the null pointer in there is a little bit safer. I've also got another function here. I've got a size member function. It returns the same thing that I store in memory, and I'm using what the STL uses, size t. Const here. That const is important. So const in general means I promise not to change something. If we put it on a parameter, it means I promise not to change the parameter. In here, I'm putting const on a member function. There are no parameters, so I can't be making a promise about parameters. I'm making a promise that this member function wow, that's terrible writing. This member function will changes no member variables. So that's a promise that this member function will never change a member variable. And that means it's safe to call it, like if I give you a const reference to my array object and you accept it as a const reference, it's safe for you to call the size member function. But if I don't put const there and you receive a const reference, you can't call size because it doesn't make a promise. You made a promise not to change the object, but you made a call to a member function that might break the promise. Okay, and then we're going to add other member functions in the following slides. And when I say we're going to add them like between line 14 and 15. We're going to just implement them inside of the class. That way we don't have to say array : and stuff like that. Now, class or struct, here I used a class because I'm going to have private data and some public member functions. So here I made it class just because I like to declare my member variables first. If I made it a struct, I could put the public member functions first and then the private data last. If I made it a struct, I could still say private, here's my data, public, here's my functions. It doesn't matter. But I tend to use class when it's going to have private data and public functions. I tend to use struct when everything's going to be public. But there's no difference in size or speed or anything else. Okay, well, we better write a copy constructor. So if I'm writing my array class, I better write a copy constructor. So here's a copy constructor. So I say, hey, you want to copy array object A? I'm going to initialize my length, I'm going to initialize my data, and then I'm going to front and for loop to copy the data. One element at a time. Wait a minute, how can I look at some other array object here? How can I look at some other array object's data that's private? Easy. I am part of the array class. The array class is one big happy family. We don't have secrets from each other. We have secrets from the outside world. So member functions are allowed to look at other objects of the same class and examine the private data variables. Okay, so we copy everything out. This works fine for lines 7, 8, 9, and 10. So 7 and 8 create two different arrays. Line 9 says create me array object C off of B. Line 10 says create me array object D off of B, make a copy of what's in B. Line 11, though, needs an operator equals. We better write an operator equals. So if we're going to write an operator equals, we're going to have to, before we do that, time O of n time. We've got to run the loop n times. Loop runs n times, it's O of n time to copy. Now, better copying. Better copying is a little bit better. I made a copy from function. Don't look at this slide. No, no, no. This is better. Let's go to best. This is how 280 might have done it. We're going to do it a better way. We're going to do it the best way. So in the best copying here, we're going to get access to swap. Somebody else convinced me the other day that swap was part of algorithm. That was wrong. I didn't go back far enough. Swap was part of algorithm up to C++11. Since C++11, it's been part of utility. And since C++17, it's been part of string viewer or something like that, which is dumb. But anyway, it's, at least for the version we're using, it's in utility. So here's my copy constructor. Copy constructor is exactly the same as it was before. So that we've already seen. That's the same. Same as the previous slides. Not this slide. That slide we don't look at. But it's the same as this version here. So this version here, that's what we're saying it's the same as. So then when we do operator equals, we are going to do what's called the copy swap method. So the copy swap method, what it says is, first, create me a copy of the other object. So I'm trying to say something like x equals y. Y, other is an alias. Other is a const reference to object y. It says make me temp that's a copy of y. Then swap my length with temp's length, swap my data with temp's data, and then return an object. Now let's look at what's really happening here. So if I say in my main, I say something like, I've got array object A has 4 elements, okay? And I put some values in there, and I've got array object B has, let's say, 7 elements. Okay, so in memory, I've got A has 4 elements, and A actually has a 4, and it's got an array of size 4. And B, so object A is all of that stuff. Object B has a 7, and it's got an array of size 7. That's what's in memory. Now, what happens when I say A is equal to B? Well, when I say A equals B, it calls the operator equals. It's the same as saying A, call your operator equals with B as the parameter. It's the same as doing that, and that tells us who's the current object. A is the current object, B is other. So when we talk about other, other is just another name for B. So when I'm talking about other, I'm talking about object B. So then, let's go back to the code. Well, I know the code. You can view them both at the same time or look at one screen and flip back and forth. So next thing we do is the first line says, create me object temp off of object other. So now let's change colors again. So object temp gets created by calling copy constructor on object other. So temp gets a 7 and a block of memory of size 7. And it would copy the elements. So if there was like a 2, 3, etc. down up there, then down here I would have 2, 3, etc. So I'd get copies of the 7, I'd get a block of memory of size 7, and I'd get a copy of all those elements. Copy constructor does all of that. Okay, then the next line of code says, A, swap your length with temp's length. Okay, so when we get to the swaps, we say put the 7 there and the 4 there. Now it says A data, swap data, A's data with temp's data. But we got to remember one thing about this is A doesn't have an array inside of it. Array A object has really, let's just take a step back here, what A really has inside of it, A has a size and it has a pointer over to here. And temp, what's really inside of temp is this. It's got the number and it's got a pointer. So when we swap the pointers, what happens is now A points over to here and temp points over to there. Now we get to the end of the function. Let's worry about the return in just a minute. When the function ends, temp gets destroyed. When temp's destructor runs, it gets rid of that block of memory. A's old block of memory gets destroyed by the destructor, and then we're done, except for the return. What gets returned? The current. So A's old data. So A's old block of memory got destroyed, but A now points over here. We return the current object by reference. We don't make a copy of it. So this is a pointer to the current object. Dereference this is the current object, and we return a reference to that object, and we get the original output. Now, why did we do this? Why didn't we do the bad way to do it? One reason is the bad way to do it has the idiot check. The idiot check is to prevent us from doing things like x equals, or actually, let's say A equals A. We don't want A equals A to go deleting the only copy of A's data. So we've got that idiot check. Everybody pays the cost of the idiot check. In this one, there's no idiot check. So now it used to be in the old way of copying, so the old way for operator equals, everybody had an O of 1 idiot cost. In the new way of doing it, the copy swap method, idiots have an O of n cost. Because idiots, at line 11, idiots make a copy of themselves. So when they say A equals A, they say, ooh, I better make a copy of A. Then I'll swap A's old data with the copy's data, and A's length with the copy's length, and then I'll get rid of the original data. So now nobody pays an O of 1 idiot check cost, but bad coders pay an O of n cost. I call that a win. We've gotten rid of an O of 1 cost for everybody and made idiots pay a bigger cost. Also, the other important reason we do the copy swap method is this is going to be almost identical for any container you write. Every container you create, you're going to have to write our custom copy constructor. We've got to do this new every time. We got to write a new copy constructor. But when we write operator equals, all we have to do is change the name of that. We got to change the name of that. We've got to maybe recode our swap lines. They might have different variable names, or maybe there's 3 variables instead of 2. But I just changed lines 10 and 11, a class name, and lines 14 and 15, I just changed the names of the data members, maybe add one more swap if there's 3 data members, and I'm done. All my copy swaps look exactly the same. And so they get really easy to write because I only have to worry about really the copy constructor. The operator equals is almost always identical. So that's why we did that. Now, I know we're a little bit over time here. We'll try to finish up these slides in a few more minutes. The big 3, they did tell you that in 280. They simplified it. I'm going to tell you there's a big 5, but I'm not going to show you how to implement the other 2. But I hate lying to you. So there is a big 5, and the STL does the big 5. The STL does implement a copy constructor from an R value, which is called a move constructor. And there's a operator equals from an R value, which is called a move assignment. And the STL does this for you. The reason it's important to know this is if I do something like this, I write a function, right? I write a function vector of stuff, let's say a vector of int, function, and inside I create a vector of int v, and I do blah, blah, and then I return v at the end of the function. From C++11 and beyond, no copy of the vector is made. Before C++11, this member variable or this local variable is about to disappear, and so you would have to copy it to the return location and then destroy the original. From C++11 on, it says, hey, don't make a copy and destroy the original, just give them back the data. Give them the data and destroy nothing. And so it makes it more efficient to write things like this. You may not even realize that this is happening, but it made a huge difference in efficiency when this was introduced in C++11. So operator square brackets. So hey, I'm at an array class. I want to write an operator square brackets. I want to be able to say things like this. I want to be able to say like array object A sub 0 equals 2. A sub 1 equals 3.3. So I wrote two versions here. One non-const allows things to be changed. One const version does not allow things to be changed. Notice the const version has two consts. So this one over on the right says, I promise not to change member variables. The const over on the left really refers to, let me just extend this, this const actually refers to the const double reference. This one says the people that I give the reference to can't change it. So because the people I give a reference to can't change it, it's safe to use in certain circumstances, like this one. I say I accept an array object by const reference. I'm a new output operator. I'm going to send this array object to the screen. Oh, hey, cool. With my own array class, I can do this. Inside of it, I want to call array.size. I can only call .size if it's a const member function. And I can only call the overloaded operator square brackets if it's a const member function. So I need the non-const version to be able to do this. I need the const version to be able to do that. To say, I promise not to change it, I just want to look at it. Now you might think that in this version, here we're using the const versions. Actually, I've tried Visual Studio and G++ and LLVM, and they don't. This one, they all use the non-const version for all of them. But in this one, they all use the const version because they must. Inserting an element, not a big deal. We move everything over to make room for one. So if I say insert at index 2, I'm going to lose the 8.4 because remember, I've got a fixed size array. If we allowed growable, then we could make it a little bit better. Our time to do this is going to be anywhere from O of 1 to O of n. My best case is O of 1. I insert at the last element. Worst case is at the beginning. Average case would be in the middle. And in the middle, I've got to move n over 2 elements over, which is O of n. And that's it. Okay, sorry we went over today, and I'll see you in office hours.